Alright, this video is going to be on finding limits. So first we're going to go ahead and define what a limit is. We're going to say the limit is the value that a function, and by function we mean f of x, which is just another way of saying y. So the limit is the value that y approaches as the input, which is an x value, approaches some value. So for example, let's say we were looking at f of x equals 1 over x, and there are always multiple limits to find because you could say x is approaching 5, or x is approaching -3, or x is going on forever. So you have lots of options, but I'm going to start off with this example because it seems to be the one that makes the most common sense. So let's say I plugged 1 in for x. Plug 1 in for x, then that means my f of x, or my y value, is 1 over 1, which is just 1. If I plug 2 in for x, I get 1 over 2. If I plug 3 in for x, I get 1 over 3. Let's say I continue that pattern. Let's say next I'm plugging in 17 for x, then I get 1 over 17. Let's say I continue that pattern, and now I'm going to plug in 513 for x, and I get 1 over 513. So what you'll notice is that the bigger the number x that I plug in, the bigger the denominator of the fraction. What's going to happen is that fraction is getting closer and closer and closer to 0. It can never equal 0, because to equal 0 in a fraction you'd have to have 0 on the top, and we never will, but it's going to get fairly close to it. So like if we continued that and we plugged in 567,892, then it would be 1 over 567,892, and that would be pretty stinking close to 0. So what I could conclude with this is I could say, my conclusion is, so as x is going to infinity, as x is getting bigger from 1 to 2 to 3 to 17 to 513 to this very large number, as x goes to infinity, f of x is going to 0. So as x approaches, or as the input approaches a certain value, the function itself approaches a certain value, and the value that the function approaches is called the limit. So the limit as x approaches infinity is 0. Now there's a special notation for this, and here's how we write it. We say the limit as x approaches infinity of the function 1 over x is 0. Alright. Next, we're going to try another example. We're going to say f of x equals x minus 1 over 2x plus 1 x minus 1. And on this time I'm going to tell you a specific limit. So right here, if I wanted to, I could have said, hey, find the limit as x goes to infinity, and that would have been the answer. Here I'm going to actually tell you which one. We're going to find the limit as x goes to 1. Now, if you think about the previous problem, like if I looked up here and I said, hey, find the limit as x goes to 2, you'd be like, x goes to 2? Oh, it is 1/2. That is the y value at 2. Or if I said, find the limit as the x goes to 17, you'd say, oh, it's 1/17. So here it seems like, oh, if I want to find the limit as x goes to 1, I should be able to just plug in 1. And the answer is yes, you could, if it was possible to plug it in, which it is not. It's a hole, so we can't figure out what that is. I can't plug in 1 exactly. So what I'm going to do first is I'm going to look at the numbers that are close to 1 from the left side. And this is called the left-hand limit. And so on my calculator, I'm going to go ahead and plug in this function. So I've got x minus 1 and 2x plus 1, x minus 1, like that. And the graph doesn't really matter to me so much because that's not quite helping me, but I'm going to just use this to plug in values because I'm being kind of lazy. So a number that's to the left of 1 would be like 0.9. So I'll plug in 0.9. And I get 0.357. And then let's say I want to get a little bit closer to 1. I'm going to do 0.99 this time. I'll move this over here. And this time I get 0.336. And then if I, sorry you guys can't see that very well, and then if I plug in 0.999, then I get 0.333, sorry, that's a 4, if I round that correctly. And now let's say I'm going to put a dot, dot, dot. Let's say I did 0.999999999, so I'm doing 9 nines this time. Now you'll notice it's 0.3 repeating, and you'll notice also that it rounded that to a 1, that x value to a 1. So we're going to say 0.1, 2, 3, 4, 5, 6, 7, 8, 9. This is 0.333. Alright, so here it appears that as you're getting really close to 1, I can't actually plug in 1, but as you're getting really close to 1, it looks like the y value is approaching 1/3. So the notation for this is that the limit as x goes to 1, and we put a little negative after it, meaning 1 from the left side, because we're coming from the left side. And I'm going to put f of x here because I don't feel like writing out the equation. So instead of writing out this part, I'm just going to put this right here. So as we go to 1 from the left, we approach 1/3, or 0.333. Now from the right, this is called the right-hand limit. So here I'm going to plug in values that are slightly different. So something that's a little bit to the right of 1 would be like 1.01. And that gives me 0.331. 1.001 gives me 0.333. And if I continue this pattern, like if I do 1.00000000001, again it does the same thing. Alright, so my notation here is the limit as x goes to 1 from the right of f of x is 1/3. Alright. Now, if you notice that the left-hand limit and the right-hand limit agree, then we can say, so we're going to say left and right agree. So then we can say the overall limit, and we're going to write this as the limit as x goes to 1 of f of x equals 1/3. So I couldn't just plug in 1 originally, but once I did the left-hand limit and the right-hand limit and found that they were in fact the same decimal, or the same fraction, then I could say overall x as x goes to 1, the function goes to 1/3. Okay, one last thing to write on your paper, a side note. Note, if left and right limits do not agree, then you say the overall limit does not exist. And that'll happen sometime.